Okay, class, in the last section we talked a lot about how what we learned was an affine texture mapping technique. And there's a reason I kept emphasizing that. It's because most systems we work in actually aren't all affine. We do 3D. 3D is a perspective projection, which is a non-affine projection. So if we're using our affine texture mapping in a perspective system, we're going to get distortion. So let me spell that out. So we have this problem. And it's a big one. Our perspective projection has a divide by z. So it has that divide by z that brings things into the vanishing point, but that's not affine. So this results in a non-affine transformation. Okay, and when you do that, the parallelism and ratios are no longer maintained. Now we know this already, right? We have a vanishing point. Parallel lines, they don't stay parallel anymore, they go in. The problem is, our texture mapping method we learned is affine. So we have a triangle that's supposed to be having a vanishing point, but any texture we put on there isn't going to have that vanishing point. The parallel lines will stay parallel, and we have this funny distortion. Let me draw out how this looks. So here's a view, and imagine, here's our image plane. Imagine we have an object like this, and this is a triangle or whatever. Some of it's at the front of the scene, some of it's at the back of the scene. Maybe it's a wall in a video game. I don't know. It doesn't really matter. And then I'm going to draw a bunch of lines. Let's try. It's hard to draw straight lines in this thing. So reasonably even spaced lines result in a bigger space. Let's try that last two again. If I keep these lines straight, what you'll see is as the object gets further away, you get a bigger space on the surface. So even though on the raster, which is where we're texture mapping, we have uniform spaces, they're not uniform on the surface. Okay, so we get something that looks like this. So imagine this is our object in object space. Okay, and then of course our barycentric coordinates. Here's a point. Now after the projection onto the image plane, we do that perspective divide, we get a non-affine distortion. Now in this case, you see the top came in because maybe the top is in the distance, and so the thing is in the distance, so the top on the image plane looks really small, but the top is really far away and the bottom is really close. You get this kind of distortion. So this same point on the the equal points there, it's going to be way over here somewhere. Okay, so, and that's my raster space, my viewport, I should say. So because of this non-uniform surface coverage in relation to uniform spacing on the raster, we break this barycentric relationship. It doesn't work anymore. Okay? So the barycentric mapping breaks down. It breaks down because we rely on this being a direct mapping, but it's not, because the ratios of the triangle break. Okay, so it just doesn't work. It's broken. The center, for example, the ratios, they're all different. So what do? So our barycentric conversion is wrong. It'll work, it'll give us something, it'll just look broken. And what happens here is lines stay, for example, is one of the problems we have. They stay parallel when they shouldn't. Let's look at some slides. So here's an example of exactly what I was talking about. So this is from Wikipedia. And here's flat shading when it looks all perfect. We have two triangles that map into texture space, and we have the checkerboard. When we do this affine transformation, each triangle keeps affine. See, the lines stay parallel. And then you have this funny spot where they meet, where the barycentric coordinates map a little differently at this border. So even though they line up at the right spot, because the texture coordinates are done right, you get this distortion where this triangle solved the best it could with parallel lines, and this solved with different parallel lines. Now, if we did it with a square, and you can actually do barycentric coordinates with squares as well, as long as it's a convex shape, you can do that. You're going to find that all the lines still stay parallel. You're not going to get that conversion that we want. Correct texture mapping should look like the one on the right over here. That's what should happen. So let's look at an animation here. One of these are done right and one of them are done wrong. What's really neat about the one that's done wrong on the left, this is an affine texture map, is you kind of get like an optical illusion. If you stare at the spot where it's broken, it looks like it's sunken into the cube or something. Like your brain tries to find depth information in there, but it's just a bad texture mapping. And you'll notice it also shuffles around and moves a little bit because that mapping just is broken. Okay, the mapping is broken. The perspective corrected one on the right, that's the one that we actually want to get working for us. So that's a problem. Okay, and to sum this up, linear interpolation on screen coordinates, viewport coordinates, okay, gives a nonlinear mapping. Interpolation on the surface is exactly what I talked about earlier. We have this linear interpolation here, gives a non-linear mapping here and here. We can see it, right? You get this linear one here, and on the surface it's non-linear. So it doesn't work. We get these artifacts, and we need to learn something new.